Today, I'd like to share with you some of my work trying to bridge scales from microscopic processes to macroscopic brain dynamics. Of course, the brain operates over multiple scales, and understanding how they relate to each other remains quite a challenge. So let me begin with an analogy. In states of matter, we know that there is macroscopic behavior of the system. Either there will be a solid, a liquid phase, or a gas phase. And this depends on the microscopic interactions. Of course, the molecules are more coupled in ice and solids than they are in liquid and gas-like states. So can this be an interesting analogy to understand how the different scales interact in brain function? So in terms of brain states, we can study various levels of consciousness, for example, from deep sleep to resting wakefulness to active states where one is performing a task. We can look at the macroscopic brain activity, and what we see is in unconscious brain states, here we'll talk about sleep. The brain is very synchronous. It displays slow waves that are large magnitude and very simple, whereas when somebody is conscious and active, the signals are quite small in amplitude and rather complex. If we look at the microscopic and mesoscopic scales, what we see is that the cells are firing synchronously, interspersed by periods of silence in these inactive, unconscious brain states. Whereas in conscious brain states, there's an asynchronous, irregular activity that we can find. Now, one way to think about this is in analogy to states of matter, that perhaps it's something about the coupling between the neurons that's changed that leads to this emergent behavior of the system. So here are 3 papers you can look at if you would like to know more about this work. And today I will propose to you 2 hypotheses. One, that macroscopic signal complexity and magnitude vary together with brain state. And the second is that macroscopic differences between brain states emerge naturally from molecular changes at microscopic scale. So first we decided to define new metrics to try to tease out these relationships between the signal complexity, the amplitude that results largely due to changes in the synchrony. So the reason is historically we've relied on the ad hoc definition of bands in the power spectra, which vary confusingly between studies, and as well rely heavily on the averages between brain regions, between times, and between individuals. So we've defined a spectral energy, which is essentially the integral under the power spectrum, and a spectral entropy, which just treats the power spectrum as a probability distribution. So what you can see here is data from one subject. This is from the Human Connectome Project, MEG recordings from subjects in a resting state, whatever rest means to each individual, and while performing an NBAC working memory task in an active state. So each of these points is a 2-second epoch, where the spectral energy and the entropy have been analyzed. And what you can first see is there's a very linear relationship between these 2 quantities. And the slope and the intercept of these change quite remarkably between states. You can see in the histograms that there's an increase in the entropy in the active compared to the resting state, and then a decrease in the effective energy. So looking at 70 subjects to see whether this law continues to be found, we see that in general, yes, the spectral entropy is much higher when subjects are active, whereas the energy is quite lower. So is this specific to MEG activity in conscious states? The answer is no. If we look at EEG activity from different states of sleep, we see, again, this conserved relationship between the effective energy and entropy. If we look at a network of Kuramoto oscillators and we defined the critical region where the oscillators are not entirely coupled but not entirely uncoupled, we see that just increasing the coupling leads to an increase in the spectral energy and a decrease in the spectral entropy. But what would it mean for the brain to be more or less coupled? Of course, it's not growing and shrinking new connections to a large extent each day, to the extent that it could explain such a phenomenon. We know that just by changing the neuromodulatory state, we can go from slow waves to this asynchronous activity. In fact, you can just stimulate the release of acetylcholine, which happens normally in the sleep-wake cycle, which will lead to the desynchronization of signals. And this is due to the loss of spike frequency adaptation. So we can simulate this. We've taken an ADX network. We've built mean field models of the ADX networks that show the spike frequency adaptation. We've represented each brain region as one of these ADX mean fields. We've connected the mean fields by the human connectome based on diffusion imaging, defining the weights and the tracked lengths that give delays in the model. So just by changing the spike frequency adaptation, we can see that we go from this high entropy, low energy state to this very synchronous, high energy, low entropy state. So in fact, macroscopic differences can emerge from these simulated changes at the microscopic scale. In terms of the power spectra, we see a shift toward the delta range, which has historically been associated with unconscious brain states. We see an increase in the functional coupling, whereas in the wake-like state, the low adaptation state, we have a shift toward the higher values of the peak near the alpha range, and a decrease in the functional coupling. So now we can visualize this activity across the brain's surface. We see the emergence of slow waves that propagate on the left in the high adaptation situation, and this kind of asynchronous distributed activity in the conscious-like activity. So finally, we can ask from data in this model, changing the spike frequency adaptation, do we see this conserved relationship between the energy and the entropy? And the answer is yes. So finally, we come back to the first conclusion that macroscopic signal complexity and magnitude vary together with brain state. And it's interesting to think that this may define some kind of conservation law that may be important for understanding the transitions between brain states and potentially even neural coding. The second conclusion is that macroscopic differences between brain states emerge naturally from their simulated molecular changes at microscopic scales. Finally, thank you all for your attention. Thank you to my collaborators and my supervisor, Alain Destexhe.